Hi, it's Mr. Anderson, and welcome to Biology Essentials video number 30. This is on advanced or non-Mendelian genetics. I thought I'd start by tying together some of the things we've talked about this year already. This is a phylogenetic tree of giraffes in Africa, and two that I've pictured here are reticulated giraffe and Rothschild's giraffe. And what we find is that even though they look very similar, they actually lie on two different branches of the phylogenetic tree. And how do we know that? How do we know which giraffe is related to which giraffe? Well, we don't use simple genetics. We use something called mitochondrial DNA. Mitochondrial DNA is DNA found within the mitochondria. It's passed from mother to mother, and it's found in all offspring. And so it allows us to trace evolutionary history, but it's non-Mendelian. In other words, it's genetics that lie outside of what we would say simple genetics. And so in this podcast, I'm going to talk about some of the problems with Mendelian genetics. Not problems per se, but things that we didn't address in the Mendelian genetics podcast. First one is the idea of linked genes, or genes that are found in the same chromosome. We'll then talk about multiple genes, and this is actually one of the most important things in all of genetics. In other words, most things are not like a hitchhiker's line. Most things are not caused by just one simple gene. Next, we'll talk about how sex chromosomes can affect inheritance. The example I'll give you is color blindness. And then finally, we'll talk about non-nuclear transfer. In other words, DNA that's not even found in the nucleus.
I want color choices good as well.
Maternal. And so let's start with Mendel. Mendel studied 7 things. He studied the stem length of plants, seed color, pod shape, seed shape, flower color, flower position. In other words, he studied 7 different characteristics, and he was able to come up with his idea of independent assortment. What is independent assortment? Well, essentially it means that all of these things assort independently. All of these genes assort independently. In other words, one cannot affect it. Now, what's interesting about the 7 that he chose is that all 7 of them are found on different chromosomes. If we were to study most characteristics, he'd find that the genes would actually be found on the same chromosome. If they're found on the same chromosome, he never could have discovered this idea of independent assortment. And maybe he did find characteristics that were actually on the same chromosome and then decided not to include them. Can't be for sure. But we do know that a number of things do travel together. For example, red hair and freckles seem to go together. Why is that? Well, they're found on the same exact chromosome, and they're found very close to each other. And so they're going to travel together, and also during meiosis, crossing over is not going to be able to split them apart. And so a lot of the time when we're doing genetic experiments, if they're linked, that means the genes are on the same chromosome, or simple Punnett squares. Next, I want to talk about multiple genes, but I want to start with an example of multiple genes. If you've ever played Monopoly, what you'll find is that it's really rare to get double ones, snake eyes, sixes, but you keep getting 7. And the reason why is that we could lay out the different dice on a Punnett square. And so this is one die. You could roll a 1 through 6. This is the other die. You could roll a 1 through 6. And so if we put out all the possibilities that you could get, you'll find that certain things show up. In other words, the odds of rolling a 7, you could actually get a 7 in 6 different ways. And so if you roll 2 dice, the odds of getting a 7 are 6 and 36 or 1 in 36. Whereas the odds of rolling snake eyes or boxcars are actually 1 in 36. And so most genes aren't transferred like this. You usually have 1 or 2 types, but we do have polygenic inheritance. So let me give you an example.
What is a real? I know.
Height in a person.
What is it? What is
this? If you're like me when you were growing up, you really wanted to know how tall you're going to become. And your doctor can't tell you. And the reason why is height is caused by a number of different genes. So in this simulation, I'm going to say that it's caused simply by 3 different types of genes, and you get 2 different alleles of that gene, and that determines how tall you're going to be. And so let's say you get 0 height genes, you're going to be short. Let's say you get all 6 of the height genes, you're going to be really, really tall. And so we have this continuum of 1 to 6, 0 to 6 genes. In us, it's actually 13 different genes, a bunch of different varieties. It'd be way more complex.
Besides,
patience to make a simulation. And so let's say we take a boy and a girl who each have 3 height genes. And let's say they grow up, they have kids, and let's figure out what their kids are going to be. what do I mean by 3 height genes? Well, this one is going to be for height genes A, B, and C. He has 1, 2, 3 of the tall genes, and she has 3 of the tall genes. Now, if he were big A, big A, big B, big B, big C, big C, he'd be really tall, but he's not, because he just has 1 of those. So let's say that in the future they have kids. And we do the Punnett square for this. Well, this boy right here could produce 8 different varieties. In other words, he could have a big A, a big B, and a big C in one of his sperm. But he could also have a big A, a big B, and a little C. And I could keep doing this, but there are 8 different possibilities I've represented those across the top. And likewise, since she is hybrid for each of those cases, there are possibilities on this side. And so to kind of lay this out, if they happen to give all their high genes to their offspring, and then there are about 6 high genes in their DNA. But let's kind of step through the probabilities. So if they were to have 64 kids, we would expect that only one of those would be super short. And only one of those would be little a, little a, little b, little b, little c, little c. And so there's a 1 in 64 chance.
No, you want him. I don't want him.
A 6 in 64 and 1 high gene. A 15 in 64, and now we're getting into big numbers. In other words, there is a 20 in 64 probability of producing an offspring that has 3 of those high genes. There's a lot of different areas we can get that. And then it drops off to 15, 6, and so the odds of having, with these 2 average height individuals having a really tall short offspring are going to be really low. But if we lay all of these out, what we get is this bell-shaped curve. If you were to look at height, for example, in the classroom, you'd find that your height is assorted according to a bell-shaped curve. That implies that it's multi-genes, polygenes.
No, you don't!
For example, I'm pretty average height when I go to buy shoes. I'm a size 11. It's really hard to find a size 11 in the sale, and it's rare that they have really size. And the reason why is that I'm really average, and so the shoe company has a lot. It may be really hard to find shoes at the other end as well. But if we ever see this bell-shaped curve, which could be anything, height, eye color, skin color, intelligence, if we ever see this bell-shaped curve, it means that it's not caused by one gene, it's caused by polygenic inheritance. And doing Punnett squares gets really out of control when you're trying to do Punnett. Next, I want to talk about sex linkage, and the person who really came after Mendel and discovered that everything he had discovered wasn't all of it. It was Thomas Hunt Morgan, and he crossed fruit flies. In this cross, he crossed females with dark eyes with males with light eyes, and he got all offspring with their dark eyes. So that makes sense. But in the next cross, he crossed these females with males, and what he found is that all of the female offspring had dark eyes, but half of the males actually had this light mutation. And so he saw a difference between the gender. And so that puzzled him a little bit. He also discovered linked genes, but what he figured out was sex linkage. There are certain genes that are actually found on the sex chromosomes, the X, and sometimes the Y chromosome. And so that gives us sex linkage. Let me give you an example of this in humans. In humans, there are 3 different pictures. Each of these have a 2-digit number. And so pause for a moment and make sure you figure out what each of these are.
49,
So
56.
let me flip over those letters, and it should have read 37, 49, and 56. Now, I'm colorblind, and I'm colorblind this type. In other words, I could see 37, I could see the 56 and kind of trace that. But I have no idea where the 49 is because I can't see certain shades of green, or I have decreased sensitivity to this green. And that's because I'm colorblind. And I'm missing a gene on my X chromosome. And so how does that work? Well, I got it from my mom. And so my mom is a carrier. Remember, your mom has 2 X chromosomes, your dad has an X and a Y. And so my mom is a carrier of that colorblindness. Now, if I test her, she's not going to be colorblind. That's because she has another gene on the other X chromosome that's totally good. And so if we show what are all the offspring that we could get from this, well, this would be a carrier who's a girl. This would be a normal girl. And actually, my sister is a carrier as well because some of my nephews are colorblind. And so if we go to the next one, this would be me.
Not so fast, Lucas. must be alone here in a place.
And so I'm colorblind. That means that I got the gene from my mom.
Here. And
What did I get from my dad? Just a Y chromosome. And the gene happens not to be located in there. So colorblindness is an example of that.
This?
If we look at my sister, is she colorblind? No, because she got a good one as well. And so in males, roughly 1 out of every 10 males are colorblind. But to be a girl and colorblind, it's an odds of 1 in 10 times 1 in 10 or 1 in 100.
I have a hair
so it's
to do
rare
it.
that I find kids in my classroom, girls that are colorblind.
I'm not really
very common to be boys. And that's because girls have this extra X chromosome. It's like a backup copy. If something goes wrong, they've got that extra. Hemophilia is an example of that. It's a sex-linked chromosome, sex-linked gene. We find it way more common in males than we do in females. Now, I'm still talking about DNA that's found in the nucleus, but there's also what's called non-nuclear inheritance. In other words, the mitochondria inside you have their own DNA. So they have their own.
This is not good.
DNA is in this picture.
This is very good.
They have their own DNA because we think they came from bacteria. And so that is passed, not within the nucleus, but it's passed actually within the mitochondria as they divide. Plants, the DNA in plants as well is non-nuclear. So it's not from the nucleus of the plant, it's actually found in the chloroplast itself. And so as mitochondria make copy after copy after copy, that DNA isn't inside our nucleus, it's actually found inside the mitochondria. And so you might think to yourself, well, how did I even get my mitochondria? Those mitochondria were in that egg of your mother. And so the DNA is passed from egg to child to egg to child. It's passed maternally, so passed through females, down through generation after generation. The neat thing about it is there's no crossing over, there's no meiosis. And so we can look at changes within that mitochondrial DNA. We can see mutations, and then we can trace evolutionary history, just like in the drafts I talked about at the beginning.
Primary and secondary, please make them stop. I think alone you were.
But it's hard to do simple probabilities for simple
What is a real
genetics like this. And
That's
I hope
included.
that's helpful.